All right, so tell me, what's the advantage? What's the advantage of having user threads that can get linked to a kernel thread? And what does it let us do that we couldn't do before? Okay, well, they could get CPU time before. How are they getting CPU time differently now?
Because the kernel has higher security clearance. They can bypass the bouncers, and there's a higher likelihood that they'll get onto the CPU.
Okay, why is there a higher likelihood they'll get onto the CPU? Okay, who were they splitting time with before? Who spawns a thread? A parent process? Parent process spawns a thread, or a process. They call it parent process, whatever. So a process spawns a thread, and by default, those threads share what? They share the CPU time with the CPU time that's already given to the process that spawned it, right? Okay, that's the default state for a thread. Okay, so now by giving threads, so threads live in user space, and more specifically than that, threads live within the environment provided, it's almost like a doghouse, provided by the process that spawned it, right? So threads live in a very tiny little world. Okay, they live inside of a process which lives inside of user space, let's say from a thread's perspective. By linking a thread to a kernel thread, okay, so one thing you said is that it gives us access to things more at the kernel level, lets us bypass the bouncers. It's kind of almost like going through pre-check security at the airport. You know, if you get the little card, you don't need to check, you just zip right through, right? So you've kind of been pre-cleared, if you will, if you're linked to a kernel thread. But then the real benefit that you get now is in the situation where we have extra CPU time, a CPU that's not being utilized, which is most of the time, right? And we talked last time about CPUs being, as we get to more and more cores, the likelihood of a CPU being available goes up, correct? All right, so if we have a CPU just sitting there doing nothing, it would be nice if we had the ability to schedule a thread to run on that CPU, even though that thread's parent technically wasn't allowed on the CPU right now. Something like that, right? So higher probability it's going to get CPU time. Threads get starved out less often. Everything should kind of shift through the system more quickly. All right, so this kind of operates on the other side of the coin. On one side of the coin, the end user we want the end user to be faked out. And part of the way human beings approach problems is we like the idea of fairness, right? So every process gets its own little chunk of CPU time, and it's like, okay, you get 10 microseconds, you get 10 microseconds, you get 10 microseconds. Everybody's being treated fairly, okay? But we don't necessarily care about that as long as we perceive it's being fair. We'd rather somebody get a little extra CPU love than the CPU sit there idle, right? So that's the advantage of linking to a kernel thread. We talked about a couple different models last time where we can have every single thread associated with a single kernel thread. We can have every single thread associated with multiple kernel threads, or we could have multiple kernel threads associated with multiple user threads, kind of upping the chances, right? You know, the more often it happens. So what in the situation where we have one kernel thread potentially associated with several user threads, then what ends up happening is that kernel thread becomes his own, like, godparent, if you will. Christian worldview? okay, its own godparent of that thread. So the thread can either share in the CPU time allocated to the parent process, or now that thread is also sharing in the CPU time allocated to the kernel thread that is getting scheduled on a CPU when available. Okay, lower priority. You know, threads are, they're not promised extra CPU time, but if it's available, we'd like to give it to them. Kind of the idea. So that would be one model. Another model would be that we have a thread scheduler where a whole bunch of kernel threads are basically scheduled similarly to how PCBs are scheduled, processes are scheduled. And each of those kernel threads then gets its own CPU time, and maybe it's just linked to one user thread. Now, right off the bat, we might think initially that that is better, right? That if we have a one-to-one type of relationship, or a many-to-one relationship where every user thread is linked to multiple kernel threads, that kind of ups their chances, right? That might be a better model, because now it's like, okay, well, I'm not competing with the 10 other threads that have the same godparent, right? You know, I'm not just one of his 10 godchildren. Now I'm, you know, competing for whatever CPU time he's allotted. Now, whenever the godparent gets CPU time, I get that CPU time. It's just a direct link. That sounds better, right? Why might that not be better? No, I mean the kernel threads don't necessarily do anything else other than support communication for the user level threads.
If one of those like child threads that are related one-to-one with a kernel thread, if one of them has to finish before another one can actually do anything, where they need a shared resource and memory, then a like 2-to-1 or like many user thread to one kernel thread might be more desirable because it can share the same memory space.
Okay, when we think about inefficiencies on the CPU, what's our main culprit of inefficiency on the CPU? What's the one necessary evil that has to be there, but we want to minimize? There's only one correct answer to this. Context switching, right? Okay, context switching, we need it, but it's bad. It takes a lot of time. We have to context switch every single time whatever's currently on the CPU can't do something else, right? That is either it ran out of time, which that's just natural selection, I guess, at that point. All right. Like, okay, well, we've given you 10 microseconds, you're out of time, go get back in line.
Isn't that a negative Christian worldview?
Well, we're saying it's bad.
Oh, okay.
So I think we're okay. Okay. Or it's going and has to, go into the device queue, get some I/O, something like that. So from a minimizing context switching perspective, if one kernel thread was given 10 microseconds and he was in charge of 10 child threads, and one of his child threads needed to enter the device queue, he doesn't have to context switch out. He can just hand over he can just shift one of his other user threads onto the remaining CPU time. So we actually minimize context switching in that scenario, right? Or at least do a halvesy context switch, where we only allocate aspects of the CPU, but we don't actually pack the bags up completely and have to unpack somebody else's bags. We just do kind of a quick swap. Save these variables, reload these variables, but we never actually left the CPU, so that's all just updating RAM or something like that, right? Okay. I got your excuse. I'll excuse you from it. With a 0.
Starting the Monday off right.
You were helping a faculty member?
Huh?
You were helping a faculty member?
Yep.
Who?
My course.
Oh, he doesn't need help. All right. So, in any case, having multiple user level threads associated with a single kernel level thread may actually be not as bad as it immediately seems, right? But on the other hand, now you have individual. So let's say there aren't. In that last example, let's say there isn't a situation where one of the threads needs I/O or something like that. So now we have 10 user threads associated with one kernel thread. And if the kernel thread's going to treat each of those child threads fairly, it's going to give, and let's still use this idea of 10 microseconds, right? Then what it's going to do is it's going to assign 1 microsecond to each of those 10 child threads. So now those 10 and internally there we have some lightweight mini context switch, right? something has to happen in order for one thread to kind of take over the CPU versus the other one. It's not as expensive as a full-blown context switch, but has a cost associated with it. So in that example, maybe that's worse, because now he has to share his allotted CPU time with all of his child processes or child threads, subordinate threads. And you have some time inefficiencies there. So maybe you're only using the CPU at 70% efficiency because of the mini context switching, something like that. Which do we choose?
Quick question. You're calling them child threads. They aren't really child threads of the kernel threads, correct? Because
They're just associated.
Okay.
Yeah. Well, they're really not. It's never a child thread. That's really a phrase that really doesn't officially exist. It's just the phrase I'm using.
Okay.
A thread is a thread, and it was spawned by some process. So we could, I guess, say it's a child of that process, but it is a thread. It's not a full-fledged process. So usually we would say a child is a process that was spawned by another process, where threads are worker bee type things.
So with deciding between the two, wouldn't it just be like situational dependent on what we want that program to do or what that our specific operating environment is doing?
Well, sure, but how do we pick?
Well, you could divvy up different ways, like in the case of if you know specifically like the program you're writing is heavy on I/O from like a disk drive or something, you might do a many to one.
Okay, so if you do know a lot about a specific application, you might be able to make an educated guess. So I mean, this is still, we've kind of thrown science out the window, like we've already seen with operating systems up to this point, where there's so much more with psychology and human behavior that goes into writing decent operating systems than just raw science. Like, this is the most efficient way of doing this. Really depends on how our user is going to use it. So certainly, if we're writing an application where we just know that this is heavy, heavy, heavy I/O, we can make a pretty good educated guess that that it's going to be common for threads within a kernel thread to have to go and wait. Therefore, it might make more sense to have a one-to-one relationship where that dude just gets off the CPU, allowing another guy to get on the CPU, rather than bulking up mini context switching, which probably adds up to more than a real context switch at the end of the runtime. Let's just separate them out and have a one-to-one relationship, something like that. Or even have a many-to-many relationship. Where, let's think about that. Many to one relationship where every kernel thread might manage multiple, no, other way around. Every user thread could be associated with multiple kernel threads. Therefore, even though they're going to have to do some I/O stuff, there's a better chance that they'll get CPU time sooner rather than later if the moment they're available, one of their other associated kernel threads gets CPU time. That kind of lets them cut in line, so to speak. Okay, but the punchline is, and hopefully we kind of saw this last time, that we looked at 3 different modern libraries, and each one of these libraries approaches threads differently based on those models. That one is not necessarily better or worse than the other one. It is situational. And we're coin flipping it based on what's going to give us the best average performance over time. That makes sense? So I guess the lesson there is that one thread library isn't just necessarily better than another thread library in terms of those decisions it makes. It really does depend on how that system is being used, and even then, that just gives us an educated guess. Yeah.
Couldn't it be said though that like looking forward with as fast as systems are getting, and that most of the programs we use aren't as advanced as the system can handle, that it doesn't matter as much anymore?
Well, as we keep adding more and more cores, it will matter less because even though we are spending time on one of our CPUs context switching, we have two other CPUs that aren't busy doing something. So it's not like we've lost CPU time. You know, if you have you go into a McDonald's and they have 6 registers open, and 3 of the people are incompetent on the register, but if they only have one person ordering lunch, it's probably not that big of a deal, right? You know, as long as they're at one of the registers that is doing, you know, that knows what they're doing. I just saw a picture on Facebook this last week that McDonald's has started putting their robotic cashiers in. Has anybody used one of these yet?
I want to, because I think it'll be cool.
Yeah, like you can go into McDonald's now. They're in Wisconsin, Milwaukee area.
Yeah.
Yeah, so I mean, I think I haven't gone into. They might be in Mequon for all I know. I mean, I think it's mass distribution. This is all the fallout from the fast food workers wanting $15 an hour.
You can be replaced.
And Microsoft and McDonald's just saying, well, for that price, we'll just replace you with robots that won't screw your order up. so I think you go up to it and I think you just put your own order in. Or I don't know if you do that or if you talk to it. I don't know how it.
I think you just put your own order in.
Hey, and you know, if you ever have seen a McDonald's register, it's all just pictures. Because I don't think they assume that their employees can read.
No.
So it's.
They don't. I worked at a McDonald's for like 4 days.
Huh?
It'd be a bold assumption.
It would definitely be a bold assumption. So yeah, that could be pretty interesting. Yeah, I don't know, but now you have the flip side to it. Now that McDonald's made it real. See, originally it was like a threat, right?
Mm-hmm.
You had all the people picketing, saying, "Oh, you know, we want $15 an hour because you know we can't take care of our families on this." Well, I mean, it really depends on which lens you're looking through. Some people are going to view McDonald's as like a good first job. Other people are going to view it, oh, that's my career. Well, if you're somebody who views it as a first job, you're going to say there's no way you can view that as a career. Well, if you're somebody who's trying to feed 3 kids with a McDonald's job, well, it's easy to see it as a career, right? So
that's why they
geographic locations.
Yeah, I mean, I'm not sure there's a clear way to kind of just throw it out there, but
and if you're in Germany, you might see McDonald's as a good place to get a beer.
Yeah, I guess. I'm just saying in general, I don't think this falls into one of those categories, kind of like the whole thing with the bluff here, where depending on whose lens you're looking through, the situation is going to feel very different. But you know, originally McDonald's was treating it kind of like a threat, like we'll just replace you with robots before we pay you $15 an hour. It'll be an interesting, interesting thing. Yeah, now that they actually have done it, so. I want to say good for them, but I think it's more interesting that they're doing it. We'll see what the fallout is.
I'm not sure how I feel.
Also, what I read was people are kind of taking that as like a full-time job, when really McDonald's is more meant for like part-time for like high school kids and like working there. It's more of a part-time job.
Yeah.
Right, but for every 5 people that have that opinion, you could probably find 5 people that think that use McDonald's as their main livelihood.
Yeah.
Yeah, I mean, it's really, those are tough arguments to have when people are looking at them through different lenses.
I think historically, though, like it would, like their employment history would show that a majority of their workers are late high school, early
probably
college
true.
age.
Probably
Yeah.
true. Yeah, I mean, that's the fast food industry in general, right?
Which could be where they're getting their rationalization on. They're going, there's only
Well, I don't think it's a false rationalization.
Yeah.
I'm just saying you can't necessarily say that the people who are trying to make it into a livelihood are wrong, because those are the same people who maybe can't get other jobs, and rather than be homeless living on the streets, they're going to try to do as much as they can through McDonald's, which is the job they could get. So it's just depends on whose lens you're looking through. Is the punchline? There's not a, it's easy for.
I don't like McDonald's.
Yeah, well, I mean,
I worked
McDonald's,
there for a
Wendy's, they're all the same.
week. I worked there for a week.
They're all the same. Well, you couldn't cut it at McDonald's, is what you're saying?
No, I couldn't stand it. There's too many drugged up high school kids there. Not even.
Well, if they need more career path people, that's what you're really saying then. So maybe it should be a career job. Maybe they should pay them $25 an hour. Get some decent people in there. Except the problem is now it's the public. You have to pay them more. All of a sudden, a Big Mac is now $9. How many of you would pay $9 for a Big Mac? we wait for them to go on sale. What two for was they two for the price of one or something like that? Whatever the deal they usually do is.
It was like
Buy one get one free.
$7 for a
in
Big
winter,
Mac.
it's whatever, you can buy one and then you get it for
The temperature of the day before or something like that. Yeah. So we don't even buy Big Macs at full price now. We wait until we get a coupon or there's a deal or something like that. So if they had to double the price of the Big Mac to support the wages, all of a sudden the same people who are arguing for the
Well, even then, they probably wouldn't have to make or increase like the price of it as much because the cost of a Big Mac to make is 13 cents.
well, that's fine. But if they want to maintain their margin,
Yeah,
they would.
Yeah, it's free. It's free. That's the problem.
Well, so be it. And the good thing for McDonald's is for every person that wants $15 an hour, there's going to be 5 other people who will take $8 an hour to do this.
15? Okay.
So it's unfortunate, but that's capitalism, right? Okay, so let's look at a quick example of Pthread. So this is some C code showing the Linux Pthread library. So here's this guy. So Pthreads can either be user level or kernel level. So both sides are implemented as Pthreads. It's a POSIX standard, so that's the Unix-y, IEEE standardizing body. Let's see, common in Unix operating systems, Solaris, Linux, Mac OS. So anything that kind of branched from Unix likely uses POSIX standardized libraries, and one of those POSIX standard libraries is Pthreads.
Like everything except Windows?
Well, not necessarily, because even on Unix, there's a secondary thread library that, I mean, you can do Java threads, first of all, on Unix. And there's also other thread libraries. This just is the part of this umbrella called POSIX is the IEEE Unix standard. And within there, one of their standard libraries is called Pthreads that act this way for coin flip reason is the deal there. Okay, so here's some C code if you've seen it here before. So here's an idea of kind of a value that might be shared among all these different threads. So kind of like shared memory, but doesn't need to be shared external to the process since threads live inside of a process, right? Now, what's interesting about this though is if we allow threads to move outside of a process by means of a kernel thread, don't we all of a sudden create a complication of those threads no longer having direct access or convenient access to the variables that their parent process once gave them easy access to? One of the advantages of threads living inside of a process is that they never leave the living room. They're always in the house right there. So they all have access to the same refrigerator. Okay, and they can go get whatever they want out of the fridge. Well, as soon as one of those threads runs out the door with the godparent, okay, fridge isn't so convenient anymore, right? Okay, so this becomes a challenge when we start talking about synchronization amongst threads and data sharing. So now we're right back to what we were talking about in the last section with inter-process communication. Now we have to have inter-thread communication. Right? It's like, oh, well, most of the time threads have direct access to the stuff, but what if they have CPU time? What if they're getting some extra CPU time and need access to something and they're not at home? Make sense? So now we have to have workarounds for that. So it doesn't just, we don't get anything for free. The second we try to use our CPU time more efficiently or more optimally, let's say, or more fully, we create a new problem we now have to solve. And we have to decide if that's worth it, right? Okay, so the idea here is that let's just start off mentally assuming that kernel threads don't exist right now, and so a pthread is spawned inside of a process and stays there. Okay, they would all have access to the same variable sum right here. All programs begin and end with main. So here's a example of a main method in C. This is actually evolved C because historically, if you went back to old school C, this would not be written like this. The char pointer argv array. this to be written as a char pointer argv. In fact, let's see. This might, no, it's printf there. Did they use any couts? Oh, there's printfs. So, no, this is C. Well, should have known right here where it says standard io.h. So definitely C. The C library for input output is standard io.h. But this would definitely be newer style C rather than old school C. All right, so we have a shared variable because it's global up here in the program outside of main, as well as the thread itself. So we have this function called runner. This is actually called, this is a prototype. We've mentioned that before. That when we talk at, maybe not in this class, but in other classes, that back in older languages when we had single pass compilers, we used to, you had a chicken or the egg problem. Somewhere in our code in here, we're going to call upon a function called runner, okay? And because runner isn't defined up here, it's going to be defined, I presume, later on in the code. I don't know if they'll show it to us or not, but it's somewhere later. They at least have to give us that function header so that the compiler can validate the syntax. So somewhere in here, we're going to have a function called runner that returns nothing. Actually, it doesn't return nothing. It returns a void pointer. That's a generic memory address is what this guy will return. And he takes a generic pointer parameter as an example, as an input rather. All right, so here's main. Main's going to go ahead and create, this is a struct for a pthread. So this will be its identifier. So TID, thread ID. Then here's a thread attribute. So here's two separate structs that hold information about threads. All right, we haven't actually built the thread yet. We've just created a couple of struct-based variables that allow us to hold information about these threads. All right, and then here's the, this is, did the person not give us the right command line argument crap? Because argv is for our command line argument. So if they didn't give us enough command line arguments, this is the argument count, then give us an error message saying how to use this program. Otherwise, if I can't convert the thing into the right stuff, so A to I says convert a character to an integer. That's what that guy does. So this is just error checking to make sure whoever called this program called it correctly, gave it the right command line arguments. So it's not even related to threads here. So pretend like that crap doesn't exist. So at this point, we have a couple of variables that we intend to use to hold information about this thread. All right. Then we're going to go ahead and we're going to get the default attributes associated with our thread. And we'll go ahead and initialize the thread. Then we'll go ahead and this is all part of the pthread library. These are functions that we have access to through pthread.h. Okay, we are not writing these. We're utilizing an existing library. So this is the POSIX pthread.h library. Right, so we'll use this function to generate an attribute list. So we're passing in the address of an attribute list. This guy. So here's our struct called attr, our pthread attribute. So we're going to pass in a pointer to that struct right here. Well, not a pointer. We're going to pass in the address of it. Okay, because by default, structs are passed by value, not by address. It's more of a historical thing. All right, so we'll pass that guy in with the assumption that he's going to go ahead and update our struct for us because he's changing it in memory because we specifically told him where in memory he can find it. That's what that little ampersand says. It says the address of this guy. Okay, then we'll actually create our thread. We're going to create our thread passing it the address of the struct we had for our thread ID, expecting that pthread create's going to fill in the values for that. Passing it the attributes, which have already been filled in. Passing it a pointer to our function called runner. Oh, here it is, right down here. So here's the function we want to, this is what we want to happen with this thread. This is the job this thread has. Make sense? So I refer to threads as worker bees, right? So we used an example last time about authentication. Phone rings, we pick it up, we spawn off a thread, and then he goes and does authentication. So if that was the example, this function would have authentication stuff in it. What's your username? What's your password? I'll check with the database. Yes, you're in. No, you're not. Something like that. All right. In this particular case, what this guy does is what it takes the parameter, converts it to we take our parameter, we convert it to an integer. Then we set that equal to upper. And then we have another variable I that we're just going to use here in a second. I don't know why they defined it like that. That's kind of stupid code. But so we have two integers being defined here. One called I that doesn't have a value yet. One called upper that gets this value, the integer version of the parameter. Then we initialize a sum to 0. Now sum we didn't define here because it's that shared variable up top, right? That all of our threads have access to. And every one of our threads is going to call this same function. So they're all sharing that sum variable, the guy that was defined all the way up top here. So this is almost like a singleton, but inside of a process, okay, rather than across multiple processes. So this is thread-based implementation of shared memory. Make sense? All right, so when we create our thread, we're saying, go ahead and let me know what the thread ID is of the guy I just created. Here's the address where I'd like you to mark that down. Here's the attributes. This is the address where you can find the attributes for that dude. Okay, this is what I want this thread to work on, whatever's in runner. All right, and then argv1, that's going to be the value associated with whatever was passed to this function. I don't know if they'll pass to this code. So they're saying usage. When you run this, here's the name of the program, a.out, then pass in the integer value. So bucket 0 of argument values will be a.out. Bucket 1 would be that integer value. Okay? So this is going to take the, where are we at here? We're going to pass in the integer value that was passed in, but it's going to come in as a string. So even if they enter the number 5, it'll come in as a string 5. Right off the bat, what do? We convert that string into an integer. So now it's the number 5, and we store it inside of upper. All right? So here, these two things right here, runner and this value, together give the Pthread library what they need to call this function. Here's the function I'm going to call. Here's the parameter he needs to be passed. This is the parameter we're going to throw in there that the Pthread library will throw in there. Here's the function he's going to call when he throws that parameter. Make sense? So we're kind of seeing a historical example, because Pthreads have been around for a while. We're seeing, and they're still used today. So we're seeing a historical example of how C libraries work. Remember, this predates object-oriented programming. So we're seeing all these wires laying out on the table, right? Okay, so what did we do? Well, we went to Radio Shack. They don't exist anymore, but here we bought a couple of little trinkets, a couple of widgets. One holds some information about a Pthread, and another one holds some other information about a Pthread. So I have those laying on the table right here. Okay, then I call up a buddy, the Pthread library, say, yeah, here's this trinket, make some modifications to it so when I get it back, it has the attributes in there. So he does his thing, hands it back to me. Now he's modified in some way. Okay, I'll lay that there. Then I call this other buddy up who knows how to create a thread. I hand him now my modified trinket as well as the original widget that I haven't had modified yet, along with the function. Here's the lawnmower engine I want you to work on. Okay, and here's the, well, do they have keys? Lawnmower engines don't have, riding lawnmowers have keys, right?
Yeah.
Ah, perfect. Here's the riding lawnmower. Here's the key to it. Okay. So given these 4 pieces of information, go and do your thing, and I'll check back on this PID widget here later on, because I'm trusting that you're going to put something in there for me so I maybe have access to this thread later on. Maybe it's the receipt or something like that. Okay, so the process ID, the thread ID for this guy actually. Okay, so that's how a thread is actually born right here. Okay, and then what are we doing? We're going to wait for the thread to exit. So this is blocking. This is not asynchronous communication. This is blocking. We're going to have the thread go and do this work, but I'm going to, this line right here, pthread join TID null, this says I'm going to, joining a process or thread ID says wait on that guy to terminate. Okay, so we're going to sit right here until it terminates. And once it's terminated, I know that that global value sum should have the final answer in it. Why? Because the function that the thread runs right here does that. Does that make sense? All right. So runner takes in a parameter, goes through, converts the string to an integer, starts a sum off at 0. We start I off at 1, keep going as long as I is less than or equal to, in our little example, 5. So, and then we keep adding on to sum. So we'll add 1, then 2, then 3, then 4, then 5, including the 5. When we're done, we go ahead and exit. So this kills off the thread. Notice that this guy did not return a value. We never actually returned a value. So if we did some work, who else becomes aware of our work? Our work was stored in this global variable sum that main has access to. So the parent process that spawned this thread has access to that sum variable right here. Make sense? So we're going to spawn the thread, which for some reason is going to go and do some adding for us. Not a great use of threads, but that's what this example shows, right? It's like look, I'm a little bit too lazy to add. So go and do the work. Let me know when you're done. Okay, that's what happened. And he comes back and says, okay, I'm done. Well, actually, he comes back and says, okay, I'm dead. It's a little bit more morbid, but okay, so he comes back. Okay, I'm done. It's like, okay, let me go check your work. Goes up, grabs the sum variable, says, here's the answer. I want all the credit. Okay, even though I spawned somebody to do it. Does that make sense? So you just saw code being acted out as a play. You can't pay for this type of entertainment.
Feel like you need dinner too.
Now, wasn't that more entertaining than just looking at a wall of C code?
Yeah.
And so historically looking at this, wouldn't you say that C code here looks fairly intimidating from a Java perspective? It's like a lot of asterisks and ampersands and things like that floating around. But as we walk through it, did we notice that it's all the same crap that we've done, that we're used to? With just throw a couple of, just kind of like, when you look at a foreign language, how it looks. So we'll take Pebbles as an example. So, I've seen, I don't know if I've seen you write it, but I've seen your cousin write Arabic, right? Is it Palestinian or is it Arabic that he's actually writing in? Is Palestinian a written language? Okay, so it's Arabic that he's writing. Okay. So, I didn't know. Because there are dialects over there. It's not a completely stupid statement is what I'm saying. So the written language is Arabic. To me, it just looks like squiggles, right? But if you look at it, it means something. Okay, it's because my eyes aren't used to looking at Arabic. So just like this, your eyes aren't used to looking at all these, these structs. We're not used to dealing with structs. We're not used to dealing with pointer crap. All these things are foreign to our eyes. So at first glance, this becomes kind of, intimidating. Yeah, who comments? Who comments, right? All right, so that's in there. They got some more crap in here.
No comments.
Oh, here's an example of a Win32 API. So instead of pthreads, let's hope they do the same example. I guess we'll find out here in a moment. Okay, Act 2 of the play. I just got back from makeup. Can't you tell? I'm getting little curlies back here. I have to shave my head again.
Weird, you have hair.
I
You have
know.
the same hairline too.
Yesterday at church, the pastor said, can we have all the kids come up? He says the younger Christians. So I always want to go up there because it seems like it's fun what they get to do. So my wife yells at me that I'm not allowed to go up there. And I ask her why, and she says, I'm not young. And she points out like my baldness. I have baldness going on up here and some other stuff. And it doesn't seem like it's fair. And even though I'm like, huh? Yeah. Well, but I mean, in real life though, I am relative. I'm probably, several of you are like, what do they call them? What's the word with the thing when you're like a Lutheran or a Christian your whole life? No, there's like it's like crib Lutherans or something like that. I've heard the phrase. One of my friends, he's old, so maybe it's an old phrase. But in any case, I was born Jewish, so I am, relatively speaking, a young Christian. See, I should be able to go up there with look. They did a dance. They did the thing. What is it? The clap your hands thing. Like, Jesus loves me. Clap your hands. And they did a turn around thing. That seemed fun. And then they gave us money. That was kind of funny too. Because I don't know. They had dollar bills hidden in the hymnals yesterday. Well, not hidden. It was all on the same page. And we were all supposed to take it out of the hymnal. And then when we left for the day, we had to put it into one of the buckets outside that I guess shows what ministries we're interested in at the church. So like Comfort Dog and all sorts of different things like that. I guess the one that had the most dollars in it was going to be, they were trying to measure, well, all I could think about from the Jewish perspective is, there's a whole bunch of pews here with hymnals that were completely untouched. There's at least $50 sitting in here. Okay, it's like there's a gold mine in the front of this church. The first 4 pews were empty.
So that's how you pay for your boat.
Yeah. But then to completely embarrass my wife because we had communion yesterday. So when the elder that was the usher that day, Gordon Hom, he came up to say it was our turn or whatever. So I took the dollar and I put it in his coat and told him to leave the engine running. I gave him a tip. Why shouldn't he get a tip? That's the service I want to support, not the Comfort Dog ministry. So I got in trouble for that too. Which I believe is further evidence that I should be allowed to go up there because I basically act like a kid, right? All right, see, perfect. Okay, so here's a Windows example of the same thing. So we're including, and it's also C code. See, here's our main method. So even though this is a Windows example, we're still looking at C. So we're going to include windows.h, which actually has the Win32 thread library in it. So this is kind of equivalent to the Pthread library, except Windows houses all their stuff inside one gigantic library instead of the equivalent on the Unix side would be to import or include POSIX.h. But instead, the Pthread library sits external to that. So we'll bring in the Windows crap. We'll bring in the I/O crap to print stuff out to the screen. So now we're giving ourselves, here's a function that's going to take in a void parameter called LP void. That's the type. They didn't want to call it a void pointer. They just want to call it LP void because it makes it look more in all caps. That makes it look extra scary. All right. And this guy is going to return a double word of type Win API. Well, that's just terrifying. Okay, what's this guy going to do? He's going to go ahead and he's going to convert the parameter into a double word. It's kind of equivalent to what we did before when it converted the string into an int. Now we get the binary version of this guy as a double word. So this will give us 16 bits, a 16-bit version of that. Then we're going to go from 0 to upper. Upper is their double word, I++, and we'll add something to our sum. Our sum, here's our global sum up here, just like we had in the other one. And in the end, so sum has the value. Go down to main. So again, instead of having a struct specifically for our thread ID, for our PID, what are we doing? We're storing it inside of a double word. Then we have our thread handle. So this is a way that we can deal with the thread directly. We'll go ahead and grab our parameter. This is the same if statements to find out whether or not they give us enough crap to call to build our thread. We get in here. Here's our create thread on our Windows side. So we're going to get our thread handle. That's the guy that we get to hold on to the thread. It's a handle for the thread that we get back. So create thread's going to take in some default values. Here's stack size, stuff like that. Here's the function we want it to call, summation. Here's the parameter we want to pass it, which is what was passed in by the user. And then here's our thread ID that we had before. So pretty much the same kind of crap that gets sent in, right? The Windows version of this. All right, and then we do its thing, and here's the wait. Wait for single object. Who are we waiting on? Our thread handle. We're willing to wait forever. And as soon as he's done, or as soon as he's dead, we'll go ahead, we'll close it, and we'll print out our sum.
So that's still blocking.
Still blocks. It's the same program, but written in 132 threads. Make sense? All right. See y'all on Wednesday.
So what's a double word?
Double word is a 16. A word is 8 bits. Double word would be 16 bits. In most languages. So in more modern operating systems, you possibly could have 16 and 32 for what words are in double words.